of e raised to power st, which is a complex exponential signal, in the form of e raised to power st, where s is a complex frequency. And we said that e raised to power st, we also noted down that it is in a way an eigenfunction also, if we apply it to a linear time invariant system. So if we apply it to the linear time invariant system, an eigenfunction e raised to power st, or a signal, input signal in the form of e raised to power st, and if the linear time invariant system has an impulse response of h of t, then we saw that it will result in a corresponding eigenvalue in the form of a transfer function, which we mentioned uh, as equation 1. Okay, equation 1. Okay, I think I have cut that equation 1. Equation 1 is basically here. Okay, equation 1 is basically here. I'll create a copy of it. So we found just a second. Second, I'll copy it. And paste. Okay. So we saw that we were able to obtain a corresponding eigenvalue h of s, corresponding eigenvalue h of s, or a transfer function of the system, which is nothing basically but the Laplace transform equation also. Okay, which is basically a Laplace transform equation also. Although I said I have not concluded the discussion yet, and I'll conclude it today. So we'll be discussing in this lecture Laplace transform representation. Laplace transform representation. Laplace transform representation. A second. So Laplace transform representation. Okay. Laplace transform representation. Okay. Now see, in order to see what are the various Laplace transform representations, we basically have to we seek a representation of an arbitrary signal, which is, say for example, e raised to power s as a weighted superposition of eigenfunctions e raised to power st. Okay. So we will use this equation 1 that we have formulated in our previous lecture. We can substitute in equation 1, substituting s is equal to sigma plus j omega. Okay, remember that s we discussed yesterday. Okay, s is e raised to power st is basically a signal which is complex signal, and complex exponential signal where it has a complex frequency s sigma plus j omega. S is nothing but a complex frequency. Okay, so we substitute equation s is equal to sigma plus j omega in equation 1, and using t as the variable for integration, or variable of integration. So then we will be having, instead of h of s, we will have h of sigma plus j omega. So s is equal to sigma plus j omega. So we have h of sigma plus j omega. Then integral will be same from minus infinity to plus infinity. Then you have h of t, okay, h of t or h of tau. I can keep it h of t. If I will change tau to t, it doesn't matter. Then we will have e raised power minus st, e raised power minus st, e raised power minus s. Instead of s, I will write down sigma plus j omega. And instead of tau, I have said that I'll change it by t. I'll change it by t. Okay. So then we have, instead of d tau, I will write down dt. It doesn't matter. So we can write this. Please have observe this equation very closely. H of sigma plus j omega will be equal to integration of minus infinity to plus infinity. Then I'll write down h of t into e raised power minus sigma. Okay, e raised power minus sigma into e raised power minus j omega minus j omega. This is actually e raised power minus sigma t. E raised power minus sigma t. It should be, yes, it is e raised power minus sigma t. It is e raised power minus sigma t. Yes, it is e raised power minus sigma t क्योंकि वो st है. ठीक है, then it is e raised power minus j omega t. Okay, j omega t. Then you have dt. Then you have dt. Okay, you have dt. Now see, if you compare this equation that I have obtained here, okay, if you compare this equation, उबैदा उबैदा आपको बेटा आवाज आ रही है?
Yes, sir.
आपको समझ में आया मैंने क्या किया इसमें?
Yes, sir.
Okay, all right. Now see, if we this, say for example, this equation is now equation 2. Okay, this equation is equation number 2. Say for example, this is equation number 2. Okay, now see, if we compare this equation number 2 with the general form of Fourier transform. What is the general form of Fourier transform? It is x of j omega. It is equal to integration minus infinity to plus infinity x of t e raised power minus j omega t, then you have dt. Okay, so what is x of j omega? X of j omega is nothing but it is Fourier transform of x of t. So instead of x of t, if we have then h of t, if we have h of t, for example, signal, then what will be my Fourier transform? It will be h of j omega. Okay, and that will be equal to integration minus infinity to plus infinity limits e raised power minus j omega t dt. Okay, फरहद, इज इट फाइन? फरहद बेटा ठीक
Yes,
है ये?
sir. जी
हाँ
sir.
ठीक है. ओके ओके. व्हाट अबाउट इकरा? इकरा को समझ में आया?
Yes,
इकरा?
sir.
ओके.
Yes, sir.
ठीक है. व्हाट अबाउट आबिद मजीद? आबिद रोल नंबर 5. हमाद अंद्राबी रोल नंबर 12.
यस सर.
ठीक है बेटा, ये इसमें कोई कंफ्यूजन तो नहीं है?
No,
ओके
sir.
ठीक है बेटा, देखो. ओके, प्लीज ऑब्जर्व इट केयरफुली. Now see, if we so this is general form. Okay, this is general form. It is general form of Fourier transform. चाहे ये equation लो आप और this equation, this is one and the same thing. If you compare it with the general form of this equation, you will observe that in our equation number 2, your input signal is basically h of t into e raised power minus sigma t, and its Fourier transform is h of j omega, h of sigma plus j omega. Okay, so I'll draw this conclusion here. If you find it conflicting, then you can ask me. Okay, so basically I have a signal h of t e raised power minus sigma t. If I take Fourier transform of this signal, I will obtain h of sigma plus j omega. Okay, and if I will take inverse Fourier transform, that is also true. Okay, the same thing is true if suppose I do not have this a capital H here, this is a small h. The same is true in the case this, if I have a signal h of t, if I will take its Fourier transform, then I will have h of j omega, and its inverse Fourier transform will be back h of t. Likewise, I have x of t. If I have a signal, its Fourier transform is x of j omega. It is one and the same thing. I'm just twisting, words. I'm manipulating them just to make you understand very easily. Okay. So I should say then equation 2 resembles the general form of Fourier transform. Okay. Equation 2, it basically resembles the general form of Fourier transform. So Laplace transform and Fourier transform, they have certain relationship. Okay. So equation 2, it resembles general form of Fourier transform, and it says, what does it say? What does it conclude? It says something like this. Okay. It says something like this. This is its conclusion. Okay. Or I can say, hence, I can also say then, hence, h of t into e raised power minus sigma t. Okay. It is equal to basically the inverse Fourier transform relationship of h of j omega. Okay. So what I mean to say is that if I take inverse Fourier transform of h of sigma plus j omega, I will obtain h of t e raised power minus sigma t. So maybe I'll ask my students, they will help me to write down the inverse Fourier transform equation here. Okay. So Mudassir is here, roll number 11. Beta, please help me. What should be the inverse Fourier transform relationship? Mudassir. Mudassir is here. Ifra Shabir is here. Mudassir, yes Mudassir, please turn on your mic. हाँ बताओ बेटा क्या लिखना है मुझे, इनवर्स फोरियर ट्रांसफॉर्म की रिलेशनशिप क्या होती है?
h of sigma plus j omega.
h of sigma plus j omega. अच्छा, बस इतना ही? इफरा is here.
Yes, sir.
अब इनवर्स फोरियर ट्रांसफॉर्म की रिलेशनशिप कैसे लिखी जाएगी?
So 1 by 2 pi
Very good. 1 by 2 pi.
integral from minus infinity
Then?
to infinity
Okay.
h of sigma plus j omega
Very true.
e to the power j omega t.
J omega t d omega. Okay, this is the general form of inverse Fourier transform. It is general expression for inverse Fourier transform. Just a little. So this is general form or general expression for inverse Fourier transform. Okay. So we are basically trying to relate how the Laplace transform and Fourier transform are connected to each other. Okay. Then we can write down from this equation, we can take h of t. Just a second. So we can write down h of t. H of t can be written as you have e to the power minus sigma t on the left hand side. Okay, in inverse Fourier transform equation. You can take it to the right hand side. It will be e to the power sigma t, then 1 by 2 pi integral minus infinity to plus infinity h of sigma plus j omega e to power j omega t d omega. Okay, d omega, or I can write it down as 1 by 2 pi integration minus infinity to plus infinity h of sigma plus j omega e to the power sigma plus j omega t, then you have d omega. Okay, now if we substitute, instead of sigma plus, substituting s is equal to sigma plus j omega. S is equal to sigma plus j omega. If s is equal to sigma plus j omega, what will be ds? See, I'll differentiate this s plus. I will differentiate s is equal to sigma plus j omega. So I will obtain with respect to omega. Okay, with respect to omega. So I will obtain d of s will be equal to 0 plus j omega, j d omega. Okay, so what will be d omega equal to? D omega will be equal to ds divided by j. Okay, ds divided by j. So I am using now, instead of s, I will instead of sigma plus j omega, I will substitute s. Okay, in expression that I have above. Okay, here, this expression. So I am substituting sigma plus j omega equal to s. Then I have to also change d omega. Okay, so once we substitute, what will I obtain? I will obtain h of t will be having the value of 1 by 2 pi integration minus infinity to plus infinity, then h of s, then e raised power st. Okay, e raised power st, then ds by j. So ds by j, I will take that j here. So that will be somewhere here, 2 pi j, because it is 1 by j. Okay, and what will be my limits? Limits will be so it will be sigma minus j infinity and sigma plus j infinity. Okay, sigma minus j infinity, and I'll say it here. I'll write it down here. Now the limits of the integral. The limits. Is it fine up to this point? अफनान बेटा ये ठीक है?
Yes, sir.
Okay, Rizwan is here.
जी सर।
ठीक है बेटा, ये रिजवान ठीक है?
जी सर।
ये पीछे
ओके, किसी को कोई सवाल तो नहीं पूछना है? Anybody having any question that he wants to ask? Okay. Now
Sir,
see the
repeat
limit.
this point.
Which point?
H of t is equal to e to the sigma t multiplied by 1 by 2 pi.
Okay, the last line I have to repeat. Last line.
No sir, general form of
Which one?
inverse Fourier transform की बाद जो है.
अच्छा, general form of inverse Fourier transform के बाद है. Okay. All right. ठीक है. Okay, I'll do it like this. See. Please allow me to. I have basically skipped a step here. Okay. So it is basically like this. It is now h of t will be equal to 1 by 2 pi integration minus infinity to plus infinity, then h of sigma plus j omega, but you had e raised power sigma t, okay, outside this integral. Since we are basically, we had e raised power sigma t also, okay, तो हम इस e raised power sigma t को यहाँ ला रहे थे. We had taken it here, e raised power sigma t. Okay, e raised power sigma t. तो अपना मुझे था e raised power j omega t, then I have j omega. Okay, it doesn't matter. Although we are integrating with respect to omega, so e raised power sigma t is a constant. Constant can be taken outside integral or inside integral. It doesn't matter because it will not have any effect. But I'm just trying to make a general form of expression. That is why I'm taking it inside the integral. Okay. Similarly, if you have a differential of a constant 2t, you can write down d by dt of 2t or d by twice d by dt of t. It doesn't matter. It is one and the same thing. Now see, when you have bases are same, powers can be added. Is it fine? ये कौन पूछ रहा था सवाल?
सर ये समझ आ गया, बट ये था ना माइनस सिग्मा टी, माइनस कहाँ गया?
ये माइनस था, ये इनवर्स में माइनस नहीं होता है बेटा। इनवर्स फोरियर ट्रांसफॉर्म में माइनस होता है। दिस इज अ फोरियर ट्रांसफॉर्म, जनरल फॉर्म ऑफ फोरियर ट्रांसफॉर्म। देयर इज अ डिफरेंस बिटवीन फोरियर ट्रांसफॉर्म एंड इनवर्स फोरियर ट्रांसफॉर्म। इनवर्स फोरियर ट्रांसफॉर्म में माइनस नहीं है। इज इट फाइन? ठीक है ये?
ओके सर।
इक्वेशन है जहां माइनस था वो असल में फोरियर ट्रांसफॉर्म की इक्वेशन है। देखिए ये बेसिकली दो इक्वेशंस है। एक इक्वेशन है x ऑफ j ओमेगा। अब देखिए यहाँ आपको मिल रहा है फोरियर ट्रांसफॉर्म, तो अंदर बनेगा माइनस इन्फिनिटी टू प्लस इन्फिनिटी x ऑफ t e रेज़्ड पावर माइनस j ओमेगा t dt। ठीक है, ये है फोरियर ट्रांसफॉर्म की इक्वेशन। दूसरे में यहाँ आपको मिलेगा x ऑफ t, but you are basically integrating Fourier transform x of j omega, but you have 1 by 2 pi also here. Okay, then you have e raised power j omega t dt. अब ये जो जनरल फॉर्म है ये है फोरियर ट्रांसफॉर्म की, और ये जनरल फॉर्म है इनवर्स फोरियर ट्रांसफॉर्म की। सो प्लीज नोट दैट यू हैव ए नेगेटिव साइन हियर बट यू डू नॉट हैव ए नेगेटिव साइन हियर। इज इट फाइन नाउ? ठीक है, इज इट फाइन? किसने पूछा था ये?
यस सर।
Okay, all right. Now see, I'm talking now about the limits of this integral. Okay, limits of this integral. The limits on the integral, the limits on this integral are also a result of the substitution. S is equal to sigma plus j omega. Okay, sigma plus j omega. So what will be the limits? Now see, the limits would be h of t will be 1 by 2 pi j integral of, it doesn't matter. It will be basically sigma minus j infinity, because omega will go to infinity, and it will be sigma plus j infinity. So these will be the limits. So it will be again minus infinity to plus infinity, then h of s e raised power st ds. Okay, so now see, from equation 3, where is the equation 3? We have marked in equation 3. Okay, this is equation 3 now. This is equation 3, for example. Okay, now we can see that hence from equation 3 that we have here, h of t that we are obtaining, okay, h of t that we are obtaining, we can observe that it is a function of h of s. Okay, h of s. So it is a function of h of s. Then we can say that h of s is the Laplace transform of h of t. H of s is nothing. So h of s is basically Laplace transform that I said here, equation 1 at the top. The transfer function that we obtained yesterday, h of s, it is nothing but it is a transfer function, and it is also called an eigenvalue, but it is a Laplace transform equation, general equation of Laplace transform. Okay, so that is what I say, that hence we can say h of s is a Laplace transform of h of t. Okay, hence we say that h of s is the Laplace transform, okay, Laplace transform of h of t. And what is h of t? H of t is inverse Laplace transform. Inverse Laplace transform of h of s. So basically this discussion was all about to find a general expression of Laplace transform and inverse Laplace transform. So h of t is nothing but inverse Laplace transform. अगर आप इसको कंपेयर करेंगे इनवर्स फोरियर ट्रांसफॉर्म के साथ, वहां पे 1/2 पाई हुआ करता था, लेकिन यहाँ है 1/2 पाई j. Okay, it resembles to that, but it is quite similar. Okay, it is quite similar. And also please note here, in this equation, yes, here in equation 2, if you compare equation 2 with equation A here, okay, equation A here, okay, yeah, this equation, इस equation के साथ अगर आप देखोगे equation A, let us not call it, you will say that Laplace transform, Fourier transform is basically equal to Laplace transform when the sigma will be equal to 0. देखिए जब equation 2 में sigma will be equal to 0, then it will reduce on left hand side h of 0 plus j omega. So it will be h of j omega. What is h of j omega? It is Fourier transform. H of j omega is nothing but Fourier transform. Then integral minus infinity to plus infinity h of t into e raised power sigma is 0. Real part is 0. E raised power 0 t means e raised power 0 means 1. Okay, e raised power 0 means 1. So it will be integration of h of t e raised power minus j omega t dt. So you will say that Laplace transform is basically, you know, if we take the real part in Laplace transform, real part, that is sigma equal to 0, it reduces to Fourier transform. मैं इसको आगे भी और एक जगह highlight करूँगा, but they are quite related. Okay, they are quite related. So this is inverse Fourier transform, inverse Laplace transform equation, equation 3, whereas equation 1 was Laplace transform equation. Okay, so we have now two equations. One is Laplace transform, and this is inverse Laplace transform equation. We can also say that equation 1 indicates equation 1. Where is equation 1? Equation 1 is at top. That is the transfer function. Okay, equation 1 is the transfer function, which is basically Laplace transform equation. Equation 1, it indicates how to determine inverse Laplace transform. Inverse Laplace transform, because we extracted the inverse Laplace transform equation from Laplace transform equation, that equation number 1. So we can now then conclude this Laplace transform of any signal x of t is given by, it is given as x of s. X of s is the representation. Okay, and it is equal to minus infinity to plus infinity x of t into e raised power minus st dt. So this is Laplace transform general equation. And what is the inverse Laplace transform equation? And the inverse Laplace transform and inverse Laplace transform of x of s, because inverse Laplace transform will be taken from x of s. Okay, so it is given by general expression. We will obtain x of t there. It is given by general expression 1/2 pi j integral sigma minus j omega. Okay, j infinity and sigma plus j infinity, then x of s e raised power st ds. We can also represent them in this form: x of t, when you take its Laplace transform, it will give you x of s. And when you take inverse Laplace transform of x of s, it will give you x of t. Is it fine? कोई सवाल तो नहीं है किसी को? रिजवान बेटा ठीक है ये?
जी सर।
रिजवान कोई
जी
सवाल
सर।
तो नहीं है? Do you have any question in that?
नो सर।
Okay. What is region of convergence? Rizwan, what is region of convergence?
जहाँ पर सर मीट होते हैं ग्राफ्स।
क्या मीट होता है? कौन से ग्राफ्स? कौन से ग्राफ?
सर सिग्नल के जो ना हम बनाए फंक्शन जो दी की होगी।
हाँ तो
उसकी
उसकी सिग्निफिकेंस, what is the significance of region of convergence? आपने पढ़ा है ये बेटा?
नो सर।
ओके। बुशरा को पता है? बुशरा,
जी सर।
what is region of convergence?
जहाँ पे सिग्नल कन्वर्ज होते हैं।
कन्वर्ज होती है। What does converge would mean? कन्वर्ज का मतलब क्या है?
एक ही पॉइंट पे मीट करते हैं।
एक पॉइंट पे
इनफिनिटी
मीट
से
करती
आते
है।
हैं मतलब।
अच्छा, बुरहान है यहाँ पे? बुरहान बेटा, बुरहान रोल नंबर 33 है।
जी सर।
What is region? What is region of convergence? What do you mean by
ये
region
वो
of
रीजन है जहाँ
convergence?
पर ग्राफ जो है वो कन्वर्ज हो जाए।
What does conversion mean?
सर एक ही पॉइंट पर मीट हो जाए, एक ही पॉइंट शेयर करे दोनों ग्राफ।
एक ही पॉइंट शेयर करे? No, that is not true. What about Binish 24 is here? Binish? What do you mean by region of convergence?
ग्राफ मीट हो जाए, कन्वर्ट हो जाए।
किसके साथ मीट करता है ग्राफ?
एक से
हाँ
converge हो
कैन यू प्लीज, किसके साथ मीट होता है?
come from infinity, they converge each other.
Okay. See, if you remember that I have told you that one of the limitation of Fourier transform is that all the signals are not integrable. Okay, you cannot integrate every signal, each and every signal. I said one of the example will be impulse response. I'll be giving some more examples also. So there are certain functions not completely integrable. You cannot integrate them. But I said that at that point, or in that case, in that scenario, your Laplace transform always comes to rescue. We define certain conditions here in Laplace transform where the signal is absolutely integrable. Okay. So region of convergence is basically a point where your system or your signal becomes absolutely integrable. You can capture the entire effect of that signal. I'll be representing that graphically also. I'll show you what does that mean, region of convergence. So I think we should write down something. It's very important. Then you'll be able to understand what is basically convergence and what does region of convergence mean. Okay. Now see, we have equation 3, 1, and do we have equation 2 also? So equation 2 somewhere here. Yes, we have equation 2 also. Okay, equation 2. So I'll continue this discussion, convergence and region of convergence, based on the equations that we have already derived. Okay. Now see, we noted from equation 2. Okay. Equation 2. What is equation 2? Equation 2. Equation 2 is h of sigma plus j omega. It is equal to integration minus infinity to plus infinity. Then you have e raised power h of t into e raised power minus sigma t into e raised power minus j omega t dt. Okay, j omega t dt. Yes. So we know that this is equation 2. We already derived it. And we noted from equation 2 that, what did we note? We noted that Laplace transform is nothing but Laplace transform is the Fourier transform basically. Okay, Laplace transform is nothing but Fourier transform. So Laplace transform of x of t is basically Fourier transform of x of t into e raised to power minus sigma t. Okay. We noted from equation 2 that it is Fourier transform of e raised x of t into e raised to power minus sigma t. So hence the necessary condition here, for convergence here, for convergence of the Laplace transform. What does convergence of Laplace transform mean? It means existence of Laplace transform. When you can define something mathematically with bounded values, with certain definite values, that means that function is converging. You are able to define it clearly. When you do not have a clear value for an equation, that means that that function is not converging. For example, e raised to power plus infinity. E raised to power plus infinity is entirely diverging function. Why? Because you cannot have a definite value. You do not have a definite value for that. So how do you define e raised to power infinity? On the other hand, e raised to power minus infinity is a converging function. It is not a diverging function, because at e raised to power minus infinity, you know that you have a definite value that is equal to 0. 0 is a definite value, whereas infinity is not a definite value. So I can say now, hence the necessary condition for convergence of Laplace transform, that means existence, or the defining it clearly, Laplace transform is the absolute integrability of x of t into e raised to power minus sigma t. What does that mean? That means if you are able to absolutely integrate this function, this signal, then only you can say then Laplace transform can exist. Okay. See, this is basically the mathematical expression for Laplace transform is this: x of t e raised to power minus sigma t. Okay. Then e raised to power minus j omega t dt. But in order for a Laplace transform to exist, for a Laplace transform to be defined, this function, integration of x of t into e raised to power minus sigma t, it should be absolutely integrable. It should be absolutely integrable. Okay, so that means you should be able to integrate this input. If this input is absolutely integrable and its value is finite, its value is less than infinity, it's not infinity, it is absolutely integrable, there is a finite value there, then only you can say that Laplace transform will exist for this equation. Okay, so we generally say that its integrability, okay, its integrability or its finite value also depends on the range of values of sigma. It can also depend on the range of values of sigma. ये function है, mathematical function, integration of x of t into e to the power minus sigma t, whether it has a finite integral or indefinite integral, it has a finite value after integration, can it be integrated or not, it depends also upon the value of sigma. ठीक है, मैं आगे वो आपको बताते जाऊंगा how it depends on that. So I can say that the range of sigma for which the Laplace transform converges is basically termed as region of convergence. So what is region of convergence basically? Region of convergence is basically a range of values of sigma. Okay, range of values of sigma. What is sigma? Sigma, please remember, it is complex frequency. It is a complex frequency on S-plane. If you have studied S-plane, or I'll also teach S-plane, it is a point or it is a complex frequency that is plotted on S-plane. So region of convergence basically is the range of values of sigma for which your integral is clearly defined, for which your integral is absolutely integrable, for which your signal or for which your Laplace transform exists. Outside the value of sigma, Laplace transform does not exist. Okay, it does not exist. You cannot calculate Laplace transform. So it is a range of values. It is not a point, basically. It is not a point. Region of convergence is not a point. Somebody was saying that it is a point where the function or a signal meets to a point or it converges to something. It is not basically a point. It is range of values. It is entire, half of the plane sometimes. It is a larger area, a region. Okay. So what is its significance? Its significance is that in region of convergence, Laplace transform is always defined. It is absolutely integrable. The function can be defined clearly. It will have finite values. It will have finite values. Okay, it will have finite values. Just a second. ओके ठीक है ये बिनिश ठीक है बेटा
जी सर
okay so please note that we should note it down that Laplace transform exists for signals for which Fourier transform does not exist. It does not exist. Okay. So हमने ये पहले भी कहा था Fourier transform की एक limitation है that it cannot be defined or it cannot operate on the signals which are not absolutely integrable. But in Laplace transform, we basically modify that signal in such a form so that we define a region of convergence or a region where that Laplace transform is clearly defined. Okay. And we should note down then, if sigma is having a range, it is definitely having a limited range. Sigma cannot take every value on S-plane. There will be a limited range where Laplace transform will be defined. So we can say then, I'll conclude this sentence, then I'll stop. With a limited range of sigma, we may then ensure x of t e raised to power minus sigma t is absolutely integrable. Okay, absolutely integrable. Even though x of t is not. It is possible that if you take x of t alone, अगर आप x of t को लेंगे, हो सकता है ऐसा होगा. It is not integrable. It is not absolutely integrable. Please remember that Fourier transform, it acts on x of t. Fourier transform जब हम लेते हैं general form of Fourier transform, ठीक है, वो होता है x of t पे employ. Okay, Fourier transform, like I have seen here, I have shown you here, somewhere here, just a second, at the top. Fourier transform, it basically operates on x of t alone. ठीक है, x of t पे ही हो जाता है ये. तो ऐसा भी हो सकता है x of t is not absolutely integrable, but once you make it, complex, you multiply it with e raised to power minus sigma t. You are basically modifying a signal in such a way so that it should be absolutely integrable. So with a limited range of sigma, we may ensure that x of t into e raised to power sigma t is absolutely integrable, even though x of t alone it is not absolutely integrable. Okay, it is not absolutely integrable. Okay. So I will write down last sentence and I'll stop then. However, if sigma is greater than 1, then x of t e raised to power minus sigma t, it is equal to e raised to power 1 minus sigma t, u of t is absolutely integrable. I'll stop here. I have left the discussion halfway. I will conclude it in the next lecture. I have to plot these all equations. Then I will tell you how certain functions can be absolutely integrable, and how, if a function is not absolutely integrable, then how can we modify it with certain things, with certain multiplications, so that it will be absolutely integrable. Sometimes a signal is not absolutely integrable. Fourier transform fails on that. We then modify it, manipulate the signal in such a way so that it fits in the Laplace transform and it becomes absolutely integrable, or a diverging or converging signal, not a diverging signal. ठीक है, अभी मैंने इसको conclude नहीं किया है. I'll start that. I'll derive that conclusion and I'll show you that demonstration in the next lecture. किसी बच्चे को कोई सवाल है आप पूछ सकते हैं. Do you have any question? किसी बच्चे को कोई सवाल तो नहीं है? रिजवान ठीक है बेटा?
जी सर.
Okay, I have another class now. Otherwise, I would have continued for 5 more minutes.